Hi, my name is Ali Lamadrid, and this is my Physics 2 Lab 4 video report. So for this experiment, our objective was to predict the behavior of circuits and use multimeters to measure the actual values of current and potential difference. We'll also further examine resistors and capacitors in circuits. So for the experiment, we used a virtual program to model different kinds of circuits in an ideal environment and then observe the resulting changes in conventional currents, resistance, and capacitance. So to complete this experiment, we had to use a couple of different principles, the first one being the principle of energy conservation, or the loop rule. This says that the total energy of an isolated system remains constant. We also use the principle of charge conservation, or the node rule. This is the principle that says the total electric charge in an isolated system never changes. We'll see more examples of equations of these principles later on in the video. And then finally, we use Ohm's law, which says that resistance is equal to the magnitude of potential difference over the conventional current I. So first, we looked at this series circuit and used both the node rule, which says I1 is equal to I2, and the loop rule, which says the EMF from the two batteries plus delta VR1 plus delta VR2 should all equal to 0. So we calculated and inputted our known values and solved and found that I1 is equal to I2, which is equal to 0.02 amps. Next, we created the same circuit, but in the model, and we can see that the ammeter readings match the prediction calculations, and the circuit does in fact have a conventional current of 0.02 amps. Next, we replace one of the ammeters with a voltmeter. We can see that the remaining ammeter reads 0 amps. This is because the circuit has a broken connection because the wires don't touch at the top, so the conventional current is equal to 0. Next, the voltmeter reads 3 volts. This represents the potential difference. It's positive because the red probe is placed at a position of higher potential difference than the black probe. Next, we took the voltmeter and measured the potential difference at different positions along the circuit, which is represented in the graph to the right. We can see that the potential difference increases all the way up until the position BC, and then decreases down to 0. We know that the steeper the slope, the larger the electric field at the position. Next, we added an ammeter in parallel with the 100 ohm resistor, and we can see that the ammeter reads 0.06 amps now. This is because by placing the ammeter in parallel with the 100 ohm resistor, we effectively cancel out the effect the resistor has on the circuit. This new path provides a more ideal loop for the current, so the current bypasses the resistor and travels through the parallel loop. On this slide, we use Ohm's law to calculate resistance for 4 different parts of the circuit. The 47 ohm and 100 ohm resistors both have resistance that is calculated pretty close to their predicted values, 47.95 and 102.05, while the resistance of the wire and the ammeter both equal 0. Next, we looked at an RC current that has both a resistor and a capacitor. If you look at the images at the top of the slide, you can see on the left, this represents the capacitor charging. So initially the light bulb is bright, and then as the capacitor charges all the way, the light goes out. And then on the top right, you can see pictures of the capacitor discharging. So at the beginning of the discharge, the light turns on, and as the capacitor discharges all the way, the light bulb goes out again. And then at the bottom, you can see a table comparing the charging and discharging time in seconds for both the 10 ohm bulb and the 20 ohm bulb. You can see that the bulb with the higher resistance, the 20 ohm bulb, has charging and discharging times that are a lot longer than the 10 ohm bulb. Next, we used the equation ln of delta V over delta V naught equal to negative T over RC to plot 20 seconds of measurements and discover what the RC value of the circuit is, which was 5.995 or approximately 6 seconds, which we confirmed by calculating the expected RC value at the bottom, which you can see also equals 6 seconds. So questions, what if I was doing this lab in real life and used an actual ammeter? What's different about a real ammeter and how would it have affected the circuits I hooked it up to? So a real ammeter actually has a resistance itself that would affect the overall calculations. So in the end, the circuits would have a lower current than the ideal environment because of the ammeter resistance that isn't accounted for. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would the ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? So the ideal model would predict that the capacitor would reach full charge instantaneously because there's no resistance. at all in the circuit, so the charge would reach the capacitor immediately. And then in real life, it would still be much faster without a resistor, but because the battery has some resistance itself, the overall time would be slower than the ideal model.